Hi, my name's Colin Tranter. Today I'm going to talk about analysis of passivation coatings and dye interactions in microfluidic devices. I'll talk a little bit about the coatings we use in our glass-based devices and about the quantification of these coatings with regard to fluorescent assays. Passivation of some kind is necessary in biomicrototal analysis systems. It is to prevent an inert environment, to prevent the unwanted binding or adhesion of analytes or reagents. Coatings are a robust and reusable way of doing this. Other ways involve flowing blocking agents in with the sample. While biomolecules and other reagents are sufficiently blocked, we've seen that small molecules such as fluorescent dyes are sometimes adhered to the surfaces and to these coatings. This causes a couple problems in that you can't see the sample if the dye isn't in your sample, and it causes some residual fluorescence that can cause problems if you're going for a high signal-to-noise ratio. We've developed a pretreatment that helps circumvent these problems, allowing you to view the first microliter of sample flowed into your system. This is useful for PCR devices and other similar on-chip processes. Here we flowed just the dye, just the fluorescent dye we use, into a heated PCR device, and we were able to analyze that increasing background noise over time at different temperatures. It's interesting to note that this fluorescence creep, as we've decided to call it, appears at a slower rate than the actual fluid flows through the device. We've been able to calculate a difference between the fluid velocity and this fluorescence velocity, and given your particular geometry, we were able to calculate a rate at which the coating is sticking to the walls and attaching into our system. We've used 4 different passivating coatings in our glass-based microfluidic devices. Those are dimethyldichlorosilane, DDMS, a longer chain fluorosilane, aquaphobe CM, a proprietary silicone mixture, and aquaphobe CF, the fluorinated counterpart to aquaphobe CM. These were recommended to us specifically for our purposes from the Gillespie manufacturer, and we've seen that they all facilitate PCR reaction, but the question is, which one is the best when paired with a fluorescent assay when you're trying to do analysis in the same device? While there are numerous other coatings, all kinds of specifically tailored silanes and silicones, we will only be testing the 4 that we have, but among these, I feel there are a few different modes of comparison. These kind of represent different types in a way. We have long chain versus short chain coatings, the short being the DDMS, the other ones being a little bit longer. We have fluoroterminated versus methyl-terminated, the DDMS and CM being methyl, the fluorosilane and CF being fluoroterminated. And we have a little bit of comparison between silanes and silicones, 2 of each. Before I talked about fluorescent analysis and those testing methods, I was going to talk briefly about how these coatings are applied to our glass devices. Earlier devices, including those discussed here, were produced through a technique called xerography, where a double-sided tape is patterned by cutting it and sandwiching it between 2 glass slides to form a channel. We're moving towards all glass chips produced by etching one wafer and fusing it to another. There are advantages of this over tape chips in that these are more robust, more reusable, slightly better thermal properties because there's no tape, it's all glass, and smaller feature size can allow potentially smaller sample volumes. Before either type of device can be coated, we have to plasma treat to activate the surface, yielding a sufficient number of dangling bonds in order for the dye to adhere and provide a uniform coating. This is done in a couple different ways. We use a Herrick plasma cleaner to treat flat surfaces, flat taped chips, before we assemble them. That can activate the surface, coat them, and then chip assembly. For etched chips, the typical plasma cleaner that we use can't activate interior surfaces. It's more directional. where the RIE can etch into closed channels. Soon after surface activation, the coatings are applied in solution, usually in isopropyl or toluene, to each glass surface in different ways. With the tape chips, I pipette a small amount of the solution onto a chip and sandwich it in between, similar to how the tape's sandwiched. With the all glass chips, a flow-through method is used where we flow the solution using our chip holder system. In each case, the solution is left to sit for at least 4 hours, and then the devices are baked in order to cure the coating. Each coating is applied in about 2 to 10% by volume, according to the manufacturer's specifications. And as I said, each coating can be applied with isopropyl or toluene. These solvents react with the coating molecules, converting them into silanols, which can then react with the activated surface. As I mentioned before, the adhesion of the dye molecules to these coatings is what we want to monitor, and we can do so simply by looking at that fluorescence creep by flowing only the dye by itself. There's no need for DNA to be present for this type of analysis. What we're doing is looking at basically that placebo treatment, that pre-treatment that we've come up with. We're going to do so by flowing through LC Green Plus, that's the fluorescent dye we typically use. We're going to buffer that dye solution with magnesium chloride and tris buffer. That's to bring it to the appropriate pH for the dye's behavior, and that's also the same environment that our reagents would flow through in with PCR. We flow this, we're looking at a 50 millimeter by 1 millimeter channel. We've got 3 of them on one device just for repeatability. We're flowing at 2 microliters a minute. Approximately 70 microliters are flowed per test. Each test is about 35 minutes long. We're imaging it with 300 millisecond exposure time, imaging it every 3 seconds continuously. Try to maintain consistent lighting and camera position for each trial to compare between the coatings. To get a feel for the type of data we're going to be looking at, here's a little bit of sample data showing, as we mentioned before, that fluorescence creep progressing down the channel. What we're doing really is looking at a line of pixel intensities down the length of the channel, and we're tracking the position of that front of the fluorescence over time. Now when you extract the pixel intensities, you get curves that look like this on the bottom. What I've done is track this fluorescence creep at 30% maximum value, just for some type of consistency between the different trials in case the intensities were different. After several different methods of averaging, such as we mentioned before, taking a line of pixels down the center, taking multiple lines of pixels on each image, averaging those together, doing some mathematical smoothing of those curves afterwards, and even doing some background subtraction to eliminate any kind of curvature of the fluorescence overall due to inconsistency of the lighting. We were able to average each image and to average multiple images together to track the fluorescence creep over time for each coating. So we've tracked the 4 different ones, DDMS, fluorosilane, CM, and CF. With the CM and CF, those were more consistent from trial to trial, and only about 3 trials were used each. You can see from the difference in the error bars that those are more consistent than the other two. The DDMS and the fluorosilane, there was much more error in between those trials. Those had 6 or 7 trials each, averaged together to yield this data, showing that the CM and CF, the fluorescence progresses faster in these types of coatings and slower in DDMS and fluorosilane. Now, because the fluorescence creep is faster or slower, that can indicate how much dye is being absorbed, or the rate at which it progresses indicates the rate of how fast the dye is leaving the sample, or how much dye is leaving the sample. So the takeaway here is that CM and CF, compared to DDMS and fluorosilane, are more suited for fluorescent analysis, and that the dye interacts less with these types of coatings. Now, some devices may still want to use DDMS or fluorosilane instead of these silicones, just due to other requirements of their type of assay. But this type of information can possibly spread beyond these 4 different coatings and go on to say that these 2 silicones behaved more favorably with dye compared to these silanes. So possibly silicones in general are better than silanes. Or that the methyl-terminated counterpart for each silicones and silanes behave better than the fluorinated silane or silicone. So fluorinated coatings interact stronger with this type of dye. That's most likely a charge issue. So I'll try to wrap this up in saying that we've developed a pretreatment placebo mixture to coat a microfluidic device with dye before you do any test. This allows you to view the first microliter of your sample. We've compared a few different coatings in regard to this fluorescent testing, showing that fluorinated silanes, the fluorosilane is the worst. It absorbs the most dye, and that the CM, the silicones in general, not to mention the methyl-terminated ones in general, are better in regard to this fluorescent testing. What we're moving toward is resolving similar issues in the etch chips that we use. We've got low signal, it's kind of fuzzy looking, it's hard to extract the data. We want to try an additional coating that company Dolomite has used. We want to try PicoGlide, see if that coating somehow improves optical qualities. If that's not the case, then we'll move to deeper etch chips. These taped chips are a little bit deeper than the etch chips we've been working with. That may be an issue in acquiring enough fluorescent. Sorry I wasn't able to be present for the meeting today. If you have any questions regarding this presentation, Dr. Cruz may be able to answer your questions. If not, you can email me at the email address provided right here. Thank you.